So I'm gonna do that and then go back to this. Where's the other one? The other ones. There you go. Okay. And also, by the way, guys, we don't have to like just stay at like 6:30. Like if we need to like go over or under or whatever, like totally up to you guys. Like, yeah, like I'm down to go over the whole test. So yeah, we can take our time and do whatever we need to do. Alrighty. So these first five questions weren't so bad. Yeah. Did you guys have any like questions about these first five questions that we had? Because if not, I'll just go over them quickly. Okie dokie. I'm gonna go over it. So first one, number one, um, we see here negative. So P, right? We know P represents like negative log of something, right? So P age is negative log of 10. Um, and if you understand how logs work, like this is 10, you can put this in the calculator, but it's gonna be negative one. All right, that's the first one. Second one, they give you three acidic hydrogens, right? They give you some acid that you're not familiar with, and they're asking like which of the following is true. And it's like they're comparing the different Ka's of the different hydrogens. And so the concept with this is that the first Ka of any hydrogen is going to be the greatest, and then Ka2 is going to be the second greatest, and then Ka3 is going to be the third greatest. This is because as you lose the hydrogens, um, like it's harder to lose the next one, basically. So that's why the Ka, the first one's so great in comparison to the second one and then the third one, because the first one is easiest to lose. So that's why the K is the greatest. So the only one answer that goes with that is choice A. All right. And three is conjugate acid base pairs. My trick with this is that they have to differ by one hydrogen. So they only differ by one hydrogen. Differs by only one hydrogen. So in this case, we see C is not right. C differs by an oxygen. A is differed by two hydrogens. And D is differed by two hydrogens. So B is the only one that's a conjugate acid base pair. All right. Four, it deals with an equilibrium constant expression, or it's asking you to figure out the equilibrium constant. If you guys are familiar, Ka represents like, right, it represents the like dissociation between like a acid. So it goes like water and then produces like hydronium and the anion. That's like Ka. Kb is the base one, right? So just like a little bit of recap, right? Kb goes over like it's the base, so B plus H2O yields to BH plus or the conjugate acid plus hydroxide. That's what Kb. So um, if we're looking at this question, we see here that we have an acid reacting with water, producing hydronium and the anion. But it's a reverse reaction. And so because of that, it's flipped basically. So this is like kind of like a coupled equilibria question where like because it's flipped, we're gonna put this like -1. Or in other words, like we're gonna do 1 over Ka. And that's the equilibrium constant for this. And that's just because like Ka represents, right, like the Ha plus H2O yielding hydronium plus anion, right? So flipping that would give you this reaction right there if you flip. All right, number five. Number five. So this is a very good question. All right, anytime you see these, um, like a buffer question, like they should be really like freebies, basically, right? Because when you see a buffer, you have base, you have its conjugate acid, you can do Henderson-Hasselbalch. The only issue with this question is you're given Kb. And in the formula for Henderson-Hasselbalch, it's pH equals pKa plus log of base over acid. So you need to find the Ka, which isn't so bad, right? So Kw is equal to Ka times Kb. So you just divide out Kb to get Ka. So do that. I'm going to do this on the calculator. Hello, why is the calculator not working? Can this work? Um, 1 second. The calculator is not working. There you go. So let's put, can I, there you go. Okay. 1.0 times 10 to the, hello, don't do that. Okay. -14 divided by, in the equation, it's 1.8 times 10 to the -5. And we're going to get 5.56 times 10 to the -10. So I am just going to, yeah, I'm going to write that here, but you don't need to do that on the exam, like, because it's a multiple choice exam. That equals Ka. And so now we have base and acid. And so I'm going to just plug it in, right? So negative log of this Ka value plus log of base, which is ammonia, which is 0.35, divided by acid, which is ammonium, which is 0.26. All right. And that's why I got the answer E. Okay. Any questions regarding any of these questions? All right. I'm trusting you guys to be verbal with me. All right. Like I'm not a teacher, so like this is a very chill Zoom call. And like what you guys like need, like we'll go over. Okay. So like you guys need to like be open and or talkative if you need to. But yeah, one thing I'll say about five is it's very easy to get confused with what you have and what you don't have, or like not what you have and what you don't have, but I guess like it's easy to like put the wrong values into things, right? Like if you have Kb, make sure you have Ka. In addition, like if you have a base and the acid, like you want to make sure you put it in the proper spaces. Like the acid goes on the denominator and the base goes on the top. Um, the reason why I put it as base and acid is because like it's a lot more of a general formula than simply like Ha over A minus. Because I know a lot of us can get confused by that. So that's why I do that. But anyways, all right. So we're gonna go over the next 6 to 10 questions. So I'll give you guys like 5 minutes to try to do them. Um, and yeah, we'll go over it. Let me know if you guys have questions. Alrighty, let's go over this. So, six, this is a concept question. Which of the following must be known in order to write the equilibrium constant expression for chemical reaction? If you guys like can recall, it's just basically the formula, the balanced formula. So, like, yeah, equilibrium constant expression is the key way, like the key term, right? Um, so yeah, you don't need the pressure, you don't need the rates, and you don't need the concentration. You just need the balance formula. All right. So seven is it's a kind of question that we didn't really go over this um year, I guess, but like I guess you're expected to know this, technically speaking. And I'll go over it because I think that this is a good question to go over so that you guys make sure you know it. You guys have had these questions last semester as well. So whenever you're trying to neutralize something, that's essentially like you're getting to that equivalence point in a titration, right? That means that all the base basically reacts with all of the acid. Um, yeah, like so at the titration point, right? Like this point here is when the whole thing gets completely neutralized. Um, and so the whole reason why is because all of the acid or all of the hydronium ions reacted with all of the hydroxide. And so that in some sense, what you can say is that they're equal to one another. So, with that being said, we see here we have a weak acid being titrated with this amount of barium hydroxide, and they give you 100 ml of barium hydroxide. And we see that, um, yeah, like 100 ml of barium hydroxide was necessary for neutralizing 100 ml of zero point 0.1 molar weak acid. And so we see here that there's two, like they have the same concentration and the same volume for both of these. So what does that imply, right? That implies, right, we see barium hydroxide has two hydroxides for every one molecule. So if I were to find the moles of barium hydroxide, right, um, that would be like the formula for that. So it would be like 0.02 mole of hydroxide. If there's the same amount of weak acid, that means that this like weak acid has to have two hydronium. How do I know that? It's because it's the same amount. If this reacts with this amount, while also producing two hydroxide, that also means that the weak acid must have 2 moles of that. And I can prove that a little bit. Or I can't really prove that right now, but we'll do more questions like that. Um, well, I mean, I guess like one way I can prove that is this has to be zero point 0.1 times zero point 0.1 times x, equaling 0.02, right? Because for the moles of hydroxide, they have to equal the moles of hydronium. And so x has to be 2 in this case. And so that's why the answer choice is B. You did not need to do this much work if you understood that like concept beforehand. But I'm just demonstrating it so that you guys can understand it a little bit better. Number eight, right? So now they're asking increasing acidity. And so this is based off of the binary acid base strength. And all you need to know is as you decrease in a period or a column, sorry, you increase in acid strength. And so here we see HOCl, HBr, HOBr, and HOI. So in this case, it'll be HOCl, HOBr, and then HOI, I believe. Let's see. Or sorry, increasing acidity. Or increasing acidity. My fault. Um, what's it called? Sorry, that's my bad. This is not based off binary acid strength, right? This is based off of the electron density chart. That's my fault. And so like remember with the HCl04, right, versus HCl03, right? We saw that there was an increasing electron density, which allowed the hydrogen to come off. It's the same thing with this, right? So the H like OI, right? The electron density here is like not as much in comparison to like HOBr, right? Like this electron density is a little bit greater, so that allows the H to kind of come off. And then likewise, um, what's it called? HOCl is going to be a really, um, yeah, like it's going to have a really big electron density that allows the H to break off. And so it's actually the opposite answer. So sorry about that. It's going to be choice D. Okay. Shoe. Number nine, we got this whole thing. So gaseous nitrogen dioxide forms dinitrogen tetroxide. Okay, so there you have this. All right, nitrogen dioxide is added to a 1 liter flask. And the equilibrium concentrations are these two. Okay, what is the value of equilibrium of the equilibrium constant for this expression? So they gave you some useless information here, right? They told you the amount of moles in the beginning. And that's really useless information because we don't need to know the initial amounts if we have the equilibrium amounts. So the K expression would be N2O4 over NO2 squared, right? And so we can plug in some values there. So here it's going to be 0.124, and here it's going to be 0.386. And then, yeah, we can figure out the K from that. So let's do that. Um, is this working? Do I need to reload? I need to reload. Okay. No, don't go over there. I hate these ads. All right. 0. Let's decrease that a little bit more. 386 divided by 0. 124, and this is squared. So I'm gonna do that. Let's check if everything's right. Everything looks right. So I got a value of 25.1. All right. Everything looks good. So that sounds good. All right. Number 10. 10's a little interesting. 10's asking, like, what will happen when you add sodium nitrate or nitrite? Yeah, sodium nitrite to a solution of nitrous acid. You want to be familiar with that. This is a weak base. Or even if you're not familiar with that, or yeah, even if you're not familiar with this being a weak acid, um, I mean, yeah, you should be familiar that this is a weak acid. But even then, yeah, what you can do is you can write out the equilibrium expression that you would expect with this, right? So you see here that when this acid's in water, it's going to produce hydronium plus like NO2 minus, right? That's the equilibrium expression for the acid in like whatever. So when you add sodium nitrite, you're actually increasing this amount, right? This is a Le Chantelier question, right? So if you're increasing that amount, what's going to happen is the equilibrium is going to shift to the left. And so this hydronium is going to decrease. And so because the hydronium is going to decrease, that means you're decreasing in the concentration of hydronium. In other words, the pH is going to increase because, how do you spell because? H3O plus decreases. All right. How is that? Do you guys have any questions about these last five questions? All righty. Um, yeah. Okay. Sounds good. I'll give you guys some time to do these next six questions, and yeah, we'll give you guys like I guess six minutes to do these questions. Yeah, treat it like you're doing the exam, I guess. So yeah.
Luke.
Yes.
So um for eight, when it's going um more electronegative, it's going to be more acidic. Is that only for the ternary acids, and then if it's binary, it's the opposite?
Yeah. So if it's like directly attached to a hydrogen, it's like the more like as you go down the column, um that like leads to a greater acidity, right? So HI would be really acidic and HBr would be less, and then vice versa, right? But if it's like something that where it's not attached to the hydrogen, so like in this case it's like HOBr, you go by the electron density. So the one that has the greatest electron density is going to be the strongest.
Okay, got it.
Sounds good. What is this add? All right. Anyways, let's go over this. So for 11, we see that there's a reaction occurring. Okay. So yeah, which of the following statements is true? So before we even look at those, let's just try to um, Yeah, let's just try to write out the reaction, right? SO3 plus H2O yields H2SO4. It looks like everything's balanced. So, let's see this. We see here that, oh, interesting. This is a very interesting question. Yeah. Number one, A. What is hydrosulfuric acid? This is just sulfuric acid. And the way you name it is based off the ion, right? So sulfate, right, is the ion. So sulfuric acid is the like acidic form of that ion. So A is not right. Um, and then yeah, let's see this. Sulfur trioxide acts as a Lewis acid and water as a Lewis base. Let's look at that. Sulfur probably is forming um, like two bonds with oxygen, or not two bonds. It's probably forming three bonds, while also having like a lone pair there. Well, actually, before I even do that, let's count the electrons, right? So there's 16 total electrons in this, because there's four in sulfur, and then there's four. Or is there four or six? It's six. Yeah, my bad. Sorry. Six times four. There's six electrons in sulfur, and then there's six electrons in oxygen. That's from the valence electrons. You can look at that in your periodic table. So six times four is 24 electrons. And so we can write out this reaction, or not reaction, this Lewis dot diagram. We can see here that it probably would have one lone pair or one double bond with the oxygen like that, and have like stuff like that. That's probably the Lewis dot diagram of that because it minimizes formal charge um, for most of the things and has like a negative charge on the oxygen and negative charge on one of those two oxygens. And then has or actually, no, what minimizes it fully is it having a double bond like that. I would minimize it. So like you see 8, 16, and then 24. So that's the electron. That's like the actual molecule. And then water, of course, is O, H2O, right, with the two lone pairs. And so this question is saying Lewis acid, Lewis base. Yeah, water definitely is acting as like a Lewis base in this case. And it's kind of yoinking it's attaching itself to the sulfur and then creating the sulfuric acid. Um, yeah, so I'd say B is the right answer with that. So my takeaway with 11 is you definitely want to make sure you know how to draw out these structures properly. If you guys recall, there's formal charge, and formal charge is basically valence electrons minus bonds minus single electrons. Okay, that's like the way to find formal charge. And so, like with sulfur, sulfur has six valence electrons, and so there needs to be six bonds, and there's no single electrons on top of it. So that's why it's zero. And the same thing with oxygen. Oxygen six minus two bonds minus four electrons surrounding it, and that's why that's zero. And that's why all these are zero. So you want to make sure you just are familiar with writing out these Lewis dot diagrams because it's very important for Lewis acid and base questions. All right, number 12. 0.375 nitrous acid solution is being titrated with potassium hydroxide. And the pH is, so at the half neutralization point, pH is found to be 3.15. What is the Ka of for their nitrous acid? So this is kind of annoying that he's asking this kind of question, and the reason why it's annoying is just because he does not really explain what the half neutralization point is during class, but I will explain it for you guys. If I write out like the Henderson-Hasselbalch equation, right? pH is equal to pKa plus log of base over acid. And I drew out this like half equivalent, like this equivalence graph, right? Where it's like, that's the volume. We see here, it's like, woo, right? At this point, this is the half equivalence point. What is happening there, right? What's happening is that the, like when you're reacting a like weak acid with a strong base, right? You're going to produce a buffer, okay? Right? You're producing a buffer because if you notice like the reaction, right, it's going to make this KOH and it's going to yield and make NO2 minus KNO2 and then plus water, right? So you're making a buffer up until the equivalence point. So like from this point of the graph to like this point of the graph is a buffer basically, which is why there's like that little jump and then like really resistant, right? And so at the half equivalence point, you actually have an equal amount of acid and base. Okay. You don't need to know why. I mean, you can do the math to find out why, but I'm telling you at the half equivalence point, you have an equal amount of base and acid. And so in this case, like let's say hypothetically, the acid and base are is equal to one, right? So there's one base and one acid. This log expression would just be equal to zero in this case because the log of one is equal to zero. So this is why it's zero. And so this formula, pH is equal to pK, is very important for things at the half neutralization point or the half equivalence point. In that, like, you can just simply use this to figure out the Ka. And so, yeah, they gave you the pH, which is 3.15. And so now you can figure out the pKa, or you can figure out the Ka, because, yeah, that's equal to the pKa. And so you just need to do 10 to the negative 3.15 to find the Ka. I know it's a little annoying that he never went over that in class, but now we're going over it, so it'll be good. Um, but yeah, so 10 to the negative log of 3.15. And I got this now, which is D. All right, so takeaway, make sure you know this formula. It's based off the Henderson-Hasselbalch, but it's only used for half equivalence points or half neutralization points. They're the same thing, they're synonymous. Okay? Anyways, let's go over this next one. For the solution, describe which of the following is the strongest base. So, yeah, when you do this, what's important is you need to figure out, um, yeah, the KBs of things, right? So, yeah, you don't need to know the concentrations, so they don't matter. What's really important is the K A's and KBs, right? So we see here that okay, so they gave you the Ka of two, right? So the Ka of two represents not it represents the HSO4 becoming as a base, right? Or acting as an acid, right? H3O plus yields SO4 minus 2 plus sorry, what am I doing? H2O, it's making H3O plus, right? So that's what Ka2 represents. And then Ka3 represents PO4 minus 2 plus H2O yielding H3O plus PO4 minus 3. All right. I wrote out all these things, but realistically, that's not really that important, right? What's really important is, yeah, let's just like put these two things together, right? The weaker the acid, the stronger the conjugate base. Okay. And so we see here that this is such a, like, is so much weaker than this. So this disqualifies HSO4 minus, and it also disqualifies um, SO4 minus 2. Why do I know that? Um, well, yeah, I just know that because if I were to find the KB of this KB value would be for SO4 minus 2. And this KAB value would be for PO4 minus 3. And so, yeah, we can figure out the KB value of the third one because yeah, this one, if you compare these two, the weaker the acid, the stronger the conjugate base. Um, and so, yeah, we need to figure out the Kb of PO4 minus 3, but I believe that's going to be E. Let's see. 1.0, or let's see, 1.0, oop, 0 times 10 to the negative 14 divided by 4 point, oh, let me go back. 4.8 times 10 to the negative 13. Okay. So do you see how the KB value for this is so big, right? That's why E is going to be the right answer when you compare it with ammonia, right? We know that A is kind of a silly answer, right? Yeah. So let me just clarify what I'm talking about here, right? So these Ka values, Ka2 represents this formula, and Ka3 represents this formula. The Kb values, respectively, will represent this Kb and this Kb, or sorry, like this base and that base, right? So the sulfate and the phosphate. The weaker the conjugate acid, the stronger the conjugate base, which is why when I find, like, when I compare these two values, I see that this is so much weaker than this. That's why this is like, this disqualifies HSO4 minus and SO4 minus 2. Next, you have to compare Kb with the ammonia by like finding the Kb values, and you see that um, yeah, like this Kb value is so big, right? Kb value for this is like 0.02, which is so much bigger than the Kb value of ammonia, which is why E is the right answer. All right, so let's continue. All right, consider the following chemical process at equilibrium. And so we have this reaction that's happening where basically we have an acid and a base reacting and forming an acid and a base. And we see that the K value is less than 1. K is less than 1. And so there's more reactants than products. So what does that mean? Um, yeah. So is Fa minus a stronger base than OCl minus? Well, if there's more reactants than products, that means that like this reaction's happening more in favor than this reaction. So like that's what like these arrows, that's what my arrows mean, right? And so A is technically wrong because yeah, if it was a stronger base, it would have to be the other way around. B would make the most sense because HF is um, acting stronger than, yeah, like HOCl in terms of acidity. That's why the arrow's like that. C doesn't make sense because at equilibrium, the like rates are equal. HOCl implies that it's a stronger acid. Um, so that's wrong because it's not stronger. So that's why B would be the right answer. All right, for this, let's see. We got solutions, acidic, basic, or neutral, right? So with this, we see that we have SO3. That's a conjugate base. And so because it's a conjugate base of H, like 2SO, like this is like a weak acid. That's just something you have to be familiar with. It's a conjugate base of HSO3 minus, and so this would be basic. The way I identify that is knowing that this is a conjugate base. Lithium nitrate, this is a conjugate base of a strong acid, so this is why this is neutral. And yeah, okay, so we kind of went through a lot of different like concepts here, and it seems like we went on a little longer than normal, but um, yeah, like does anyone have any questions about these like 6 questions that we just went over? If you want me to clarify anything or anything, like let me know.
Hi, Luke. It's not about one of the questions you just did, but can you go over number 7?
Number 7, perfect. Yeah, sounds good. Right. So number 7, the whole idea when you neutralize something is the moles of hydroxide have to equal the moles of hydronium. And so when you, yeah, if you see here, we have this volume of base, this concentration of base, and we see that we can use this amount of volume of acid and this concentration of acid to neutralize it completely. What that implies here, right? If I calculate like the moles of hydroxide, so like this is molarity, this is liters, and then this is like the moles of OH minus, right? We see that we have 0.02 moles of hydroxide. And so over here, if I were to multiply these three things, right? 0.1, and then this is like X value, right? This has to also equal 0.02 moles of hydronium. And so if I look at these two formulas here, right? They're like because the volumes and concentration are identical, that must mean that there has to be two protons or two hydrogen atoms within that acid. Does that make sense?
Yeah,
Okay, sounds good.
thank you.
No problem. But yeah, any other questions regarding anything?
Can you also do number 8?
Number eight, yeah, sure. So number eight, right? This is dealing with like I believe ternary acids or any acid where like the hydrogen isn't directly attached to like the like source of like the electron density, if that makes sense. So like because there's a greater electron density among like OCl as opposed to like OBr or like HOI, right? Like there's like a smaller like density. This is like a bigger density, and then this is like a huge density. It's like kind of this density is weakening this bond and allows the hydrogen to break off. So the stronger the electron density, the stronger the acid in this case. And so that's why D is the right answer. We see that the electron density increases as we go this way. Does that make sense?
Yeah, but I also saw that like on the periodic table, these like the answer is the bigger the size, the atomic size, it was a stronger acid. So can you just use that as like a general rule?
Yeah, you could use that as a rule, but it's not so much about like the size, it is more about like the electron density. It's like the same kind of like you could like imply both of those things, but like those are kind of synonymous, I guess. But I guess no, they're not synonymous. But you're saying like the bigger the atom, what was the rule that you said?
Yeah, so like I has a bigger atomic radius than
Mm-hmm.
Br. And
Mm-hmm.
like that's what I was saying. Like the bigger the atomic radius, the stronger the acid was. So is that like just a coincidence in this question, or is that actually like a rule that I could use?
Well, that doesn't really apply to this question because I has a bigger atomic radius, but it has this weakest acid in this case. I think like that applies to binary acids, right? So like HI, which is stronger than HBr, which is stronger than HCl, because I like has like I guess like you could say the biggest like atomic radius, and so like that's why this is stronger than that. And those like HBr is stronger than HCl. But like with this, because the hydrogen isn't directly attached to the like I guess the halogen or the thing that's like changing, yeah, you have to go by like the electron density rule. But like with the binary acids, that works.
Okay, okay, thank you.
Yeah, no problem. All right, any other questions?
Could you go over 14 again?
Yeah, no problem. Yeah, that sounds good. So we see here a reaction. And we can see like bronze ciliary acid base definition. This is an acid. This is a base. This is conjugate acid. This is conjugate base. And we see that the K value for this like reaction, the way that it is, it's less than one. So that means there's more reactants than products. And this also implies that like the reverse reactions happening, I guess, like not faster, but there's more like not that the reverse reaction happening more, but it's that like there is like the equilibrium causes there to be more reactants than products, meaning that the reverse reaction is like I guess stronger than the forward reaction in this case, like at equilibrium, if that makes sense. Like they're equal to like the rates are equal to one another, but like at equilibrium, there's just more reactants because of the fact that that's like a more dominant reaction. So now let's look at like the answer choices, right? We see that fluoride, right? Like they're asking which of the following statements is true. So you need to figure out like the false ones basically. If fluoride was a stronger base than OCl minus, that would mean that the forward reaction would be more favored and the K value would be greater than one. But we don't see that with A. So that's why A is wrong. And then C just doesn't make sense because this is equilibrium. There's not like it's supposed to be equal. Um, and then D is supposed to be about like I guess saying HOCl has a larger Ka value implies that it's a stronger acid. And we see here that it's not acting like that because the reverse reaction is happening, I guess, like to a greater extent than the forward reaction. Um, Not that it's happening at a greater extent, but that there's like just more reactants than products. So that's why the reverse reaction is more dominant than the forward reaction. So that's why D is wrong. And so B is the only one that's right because it's showing that because this is such a stronger acid in comparison to HOCl, that's why this like forward reaction, like this reverse reaction is happening at a greater extent than the forward reaction. Does that like answer your question?
So if the reverse reaction is favored, it doesn't mean anything about like the concentrations. It means that the products would be just stronger acid or base.
Yeah. Like when you're not dealing with like Le Chatelier's principles, yeah, like the K value, like yeah, you're not given like any concentrations or anything. It's simply like because of the K value, like that implies that the like reactants that are reacting isn't, or sorry, like the products in this case is just like a lot more like reactive than like the reactants in this case. And that's why like the K value shows that there's more reactants than products because these two species like don't want to be like they don't want to exist basically. They want to like this HF is more readily able to donate its hydrogen to OCl minus than the other way around. Like this HOCl is not as ready to donate its hydrogen to F minus. And that's just because of like its structure or whatever it may be, but you don't need to know that yet. But does that answer your question a bit?
Yeah. So then if K was greater than one, um, then it would be the opposite in
Mm-hmm.
which the reactants in this would be stronger acids and bases.
Yeah.
Okay.
Mm-hmm. Yeah. Sounds good. Yeah. Any other questions? Okay. Well, listen, guys, I know I'm not the best like explainer. So like if you need me to like clarify something or anything, let me know. But anyways, yeah, I'll give you guys 3 minutes to do these three questions and then we'll go over it. All right, let's go over these three questions. So 17 gives you a equilibrium, and yeah, let's read it out, right? The balanced chemical equation for the formation of cobalt-containing complex ion is shown. In aqueous, the presence of the complex causes a solution to appear blue. Which of the following changes will cause the solution to appear more blue? So we want to increase this complex. And so here we see removing cobalt, that wouldn't work. Increasing pressure, there's no gases, so that wouldn't work. So that means D is wrong and D is wrong. B is the only thing that will cause a reaction to shift to the right due to Le Chatelier's principles. All right, number 18. So we have this titration curve of different acids at this molarity with 50 ml of sodium hydroxide. And we see here it's 50 ml. That is, yeah, at 50 ml, like that's the neutralization point for sodium hydroxide or for all these different acids. So, which one's the weakest acid? That's going to be F. F is the highest, right? It starts off at 6, so it's like what? It's really weak. Um, 19, which pH curve corresponds to an acid with a Ka value of 1.0 times 10 to the negative 4. So this is also another example of me doing pH is equal to pKa, because I can see here like the mid equivalent, like the half equivalence point is like 25. And so whichever one corresponds to like a negative log of 1.0 times 10 to the negative 4 is equal to 4. So I need to figure out which like acid at this point like hits a pH of 4, and this is C in this case. So B is the right answer. Is there any questions regarding these questions?
Wait, can you explain 19 again? Sorry.
Yeah, so this is an example of like when to use like pH equals pKa. So I told you earlier that pH equaling pKa is used for the half equivalence point. And the reason why it's helpful is because if you know the pH at the half equivalence point, you can figure out the Ka, and vice versa. If you know like the Ka, you can figure out the pH at the half equivalence point. And so in this case, they're asking you to identify the acid that corresponds to this Ka value. And so this is like a little bit of like a hint of like, okay, like this acid has a Ka value of this of like 1.0 times 10 to the negative 4. So if I plug in pH equals pKa, right, I can see that the acid at the half equivalence point, so that's the point before, like at 25 milliliters, because 50 is the equivalence point, that like point is going to give me the, what's it called? The half equivalence point is going to give me the pH. Um, and that pH will allow us to identify the acid that we need to like identify and answer the question with, if that makes sense. So when I add the Ka value to the formula, I see that that's going to equal 4. Um, and then I just have to figure out which acid at the half equivalence point has a pH of 4. And so in this case, C is going to have that.
Okay.
Does that make sense?
Yeah, yeah. Thank you so much.
Yeah, no problem. Any other questions? Okay. All right. Let's try to do these next 6 questions. I'll give you guys some time to do it. Oh wow. Okay. I'll give you guys I'll give you guys like 5 minutes to do this. All right, let's go over some things. Can you guys see my screen?
Yeah.
All righty, sounds good. So let's see this. We got a equilibrium. So we got this UO2 and HF yielding gas and then gas. All right. A is shift right, B is shift left, C is no change, and D is cannot be determined. Um, and so for this question, um, what's it called? Yeah, let's see this. Is there any information that we need? So yeah, this is exothermic. That's really important. So whenever I see exothermic, I'll just like add like heat or temperature or whatever, right? So it's like exothermic, so it's being released, so it's gonna be like a product basically. So if I see that temperature is increasing, that means you're gonna increase the heat here, which is like basically a product. So you're gonna favor the reverse reaction. All right. If it was endothermic, I would add heat here, and that would favor the forward reaction. But this is exothermic, so it's going to be released. So the answer for this would be B. All right. Next is adding fluorine gas. Fluorine, there is no like fluorine gas on its own here. Fluorine gas is just F2. You have HF and then you have UF4. So that does nothing really. So that's why this answer turns to C. Adding uranium dioxide to the solution, uranium dioxide is this value, but the issue with this is it doesn't actually change its anything at equilibrium because it's a solid. Solids don't do anything at equilibrium. So if I were to write the K value of this, it would be like two, or it'd be H2O squared UF4 over HF to the fourth power, like that. You would not include UF2 in the equilibrium. So even if you add some, nothing's going to happen. So it's going to be C. Um, you're removing uranium tetrafluoride. So if you remove this, you're going to favor the forward reaction. And so that's going to be choice A because you need to replenish UF4. 24, the system is placed in a glass container and HF reacts with the glass. So that means that HF is being removed. So that's going to favor the reverse reaction. And so that's why B is going to be the right answer there. The volume of the container is tripled. So this is important. This is a thing. This is important. This is based off like the gas laws, right? As volume increases, pressure decreases. So pressure and volume have an inverse effect. So if volume is increasing, you can almost think of it as like pressure decreasing. And so the rules we know is that if pressure decreases, we're going to favor the side with the smallest, um, smallest number of gaseous moles. And so on the left we have 4, and on the right we have 3. So it's going to favor the forward reaction, or sorry, no, sorry. The pressure decreasing, right, would favor the side with the most amount of gaseous moles. So it's going to favor the reverse reaction, and so that choice would be B. Is there any questions regarding Le Chatelier's principles? You're definitely going to have a question like this on your exam. So make sure you know how to do it. All right. You guys should be pros at this, all right? So make sure you guys do well with this. Please let me know if you have questions, all right? All right, let's try to do these questions. I know these are true or false questions. I'm gonna give you guys like 5 minutes to do all these. All right. You guys got this. I believe in you.
For the ones that we just did, would it ever be a case where it cannot be determined?
Um, no, I don't really think that there would ever be a case where I think he's just like that's like the give up option.
Okay.
So yeah, don't put cannot be determined. There might be there might be a case where instead of it being um instead of it being like shift right, shift left, no change, it might be like increasing or decreasing, right? And they might ask um what's it called? Like if you add like heat or no, if you add like UF4 my like gas, like let's say, yeah, you're removing UF4 in the system, right? You know how like it's gonna shift to the right, right? What's like the concentration of UF4 like gonna be like now that the equilibrium shifted, right? That would be like cannot be determined, I feel like. Do you get what I'm asked like saying there?
Wait, can you say that again?
Yeah, so like let's say instead of it being like shift right or shift left, like it's like A is increasing, B is decreasing, and then C there's no change, and then D is cannot be determined, right? Let's say we're talking about like the concentration of UF4 um, when like UF4 is being removed, right? So like obviously UF4 is being removed, um, but then at the same time the forward reaction is occurring and it's replenishing UF4. So it's like what's happening with UF4? You know what I mean? Um, that's like a situation where it might be like cannot be determined, but it's honestly going to be like decreasing. But yeah, most of the time you're never going to see cannot be determined, all right? Um, but yeah, do you get what I'm trying to say there?
Yeah.
Okay, sounds good.
And it's just that it couldn't be determined because the reverse reaction is happening at the same time as the forward reaction.
It's not like when this UF4 is decreasing, right? Like, or when UF4 is being removed, the forward reaction is occurring, and replenishing UF4. So we don't actually know like how much, if it's like, if UF4 itself is increasing or decreasing.
Okay.
But yeah, I'll give you guys some time to do this true or false, and we'll go over it. Alrighty, let's go over the true or false. So bicarbonate ions can act as acids and bases. This is true, right? HCO3, right? We know it can donate a proton and become CO, or yeah, it could donate a proton and become CO3 minus 2. And it can also accept a proton and become H2CO3. So it's like amphoteric in that nature. 27, as an acid strength decreases, the Kb of the conjugate base decreases. This is false. There's like an inverse relationship with the acid and its conjugate base. As I really want you guys to write this down if you don't understand this, but the weaker the acid, the stronger its conjugate base. Okay, like that's a really important rule because you'll see that like a bunch of times in your exam probably. 28. For a chemical system at equilibrium, the rate of the forward reaction and the reverse reaction are 0. This is false. So at equilibrium, there's two things you need to know. The product concentration of products and reactants um, are constant, and the rate of the forward and reverse reaction, rate of forward reaction, it's equal to the rate of the reverse at equilibrium. This is very important because those are the two states of like at equilibrium. So yeah, it's not that they're 0, it's that they're equal. You're definitely going to have a question regarding that. So it's really important that you check it out. All right, you just make sure you're familiar with those concepts. Phenol blue changes yellow to blue at pH of 3 to 4.5. The pH will be blue with a weak acid, strong base titration. Um, yeah, so in this question, the first part isn't like a lie. I think it's true. The second part is going to be true in this case, right? A weak acid, strong base titration. What's it called? When you have a weak acid, strong base titration, you're gonna have a pH at the equivalence point that's above 7. So like pH is gonna be above 7. So like let's say that this is gonna be like 8. So at the equivalence point, you're gonna have it be blue in this case, which is what you see here. So that's why it's true. 30, HNO2 and NO3 can be used to be prepared a buffer. That's false. You need an acid and its conjugate base. This is not its conjugate base. Increasing the pH of aluminum hydroxide will increase its solubility in water. This is true. And the reason being is that when you are, this is an insoluble salt, right? So when you dissolve it, you're going to make Al plus 3 plus 3OH minus. And so when you sorry, oh no, this is false. My bad. Increasing so this is a really common mistake, right? When you think increasing pH, that means you're increasing the hydroxide concentration. So increasing the hydroxide concentration would cause the reverse reaction to happen, right? Which would make this less soluble. So that's why 31 is false. 32, the percent association of HF and this, it will be greater than the percent association of 0.5. This is true. This is based off like the concept of percent association. All you need to know is that the more dilute a weak acid is, a weak acid is, the greater the percent association. All right. If you don't know it, write it out and make sure you know it. Okay. That's just a constant concept that you know. 33, equilibrium constants remain constant. That's false when temperature decreases. We know that is false because of Kw, right? Kw changes as temperature changes, right? Triethylamine, and this is the molecule for that, can act as a base. Generally speaking, anytime you see like a nitrogen, unless it's like triple bond, or not even triple, nitrogens always act as like loose bases, like they have that lone pair. So that's why this is true. Yeah, 0.5 of nitric acid solution has a higher pH than HNO2. This is false. All of the H is going to be dissolved, like is going to come out of this, but not all of the H is coming out of this. And because they're the same concentration, I can like make that claim. And so this is going to have a lower pH. That's what would make this true. In a KOH solution, the hydronium concentration is that makes sense. You can calculate it yourself if you'd like. So if I do the negative log, oh, let's go back. If I do the negative log of 1, I'm going to get 0, which is the POH. So the pH would be 14. In other words, right, like if I do 10 to the negative 14, that's going to be equal to that. So that's why this is true. Okay. It's 37, adding Na2S to a solution of zinc sulfide will increase its solubility. This is false. Zinc sulfide has sulfide ions, right? And so adding sulfide ions will decrease the solubility, right? Because it's going to shift it to the left. So this is false. Is there any questions regarding this? Anything at all? Shout it out. Let me check if there's anything in the chat. Anything? All right. Okay. It's 6:30 now, so if you guys feel like you need to go or whatever, you guys are more than likely able to leave. But if not, like I want us to try to finish these last few questions. So I'm gonna give you guys um give you guys like 10 minutes to try to do these. Um yeah, obviously there's a not these are free response questions, so like take it with a grain of salt. He's not gonna give you guys such long questions for some of these, but yeah, just be prepared. But yeah, I'll give you guys 10 minutes for these next two questions. And let me know if you have any questions regarding anything before or anything. Hello, I'm back. Sorry, I want to go do something. If anyone had anything, let me know. And yeah, just an FYI, I'm gonna post this YouTube as a YouTube video so you guys can review it when you guys get the chance. Okay, I'm gonna go over 39, 8 and 39, and then after that, I'm gonna give you guys another like probably give you guys like 7 minutes to try to do these next questions here. Because yeah, I think you guys can do it. But anyways, so this question's a little bit involved. There's a lot of little like interchanging parts in this, but we'll figure this out. So we're asked to find all the concentrations here given, and also the pH. Um, and so yeah, let's do this. So yeah, and yeah, these concentrations at equilibrium. So one thing you need to know is you need to know KF, right? That's what it is here. And you need to figure out the moles first to figure out the concentration of potassium because potassium doesn't even react with anything. So if we look at the periodic table, we see that K, where's K? K is this and F is this. So let's add those two. So 39.098. Oh, 1 second. 0.098 plus 18.99 or yeah, 998. So that's the molar mass of KF. So you want to make sure you remember how to do that. It's a not a hard step, but just make sure you remember that. So then now you have the moles, and you want to divide it by this volume. So that's um, 0.575 liters over 1, and that gives you the molarity. So if I do 5.75 times 1 over 58.096 times 1 over 0.75. Okay. And that gives me this value. This is a concentration of KF, and that's also the concentration of K plus. So I'm going to put 0.13 here for the molar. The reason why I know that is because K plus is not really reacting with the equilibrium, right? And so, yeah, this is the concentration of F on its own, right? So like F is equal to, yeah, like initially that's what the concentration is there. Um, and so, yeah, let's write this out, right? We have HF reacting with water to produce F minus plus H3O plus. Or if anything, what is easier to do to make this easier is we can do F minus plus H2O yields HF plus OH minus. The reason why I'm doing this is because we can figure out the OH minus by doing this, right? So let's do an ice chart, and we have the thing here, it's 0.131 molar. This is water, so it doesn't count. Over here, we have 0.575 molar. And hydroxide is 0 in this case. And so this is going to be minus X, this is going to be plus X, and this is going to be plus X. And we're going to have X 0.575 plus X. And then we're going to have 0.131 minus X. So we can figure out X in this case. We have to figure out the KB. So we do KW over KA equals KB. And so that's going to be, let me do this, 1.0 0 times 10 to the negative 14, right? Divided by 6 points. So I need to put a thing here. Parentheses 6.60 times 10 to the negative 4, close parentheses, right? And we get a KB value of this 1.51 times 10 or 2 times 10 to the negative 11. That's really important. And now, yeah, we plug in these values into the KB, right? So this is equal to hydroxide, so X times 0.575 minus X over 0.131 minus X. So let's do that. So on the Y, this is a little helpful tip that I have for you. On your calculator, you can put in these values. So let's do that. 0.575 minus X, right? That's the top. And then, yeah, I always like to cross multiply. That's like my thing. So 1.52 times 10 to the negative 11 times 0.131 minus X, close parentheses. And then you do second calc, intersect. And so I'm going to do boom, boom, boom. And I got this as the X value. And so that's X. And so, yeah, that little trick there is what's really important. If I press X here and I enter it, that gives you the X value. So that's really helpful. So now we can solve. Oh, wait, did I make a mistake? I think I made a mistake. I made a mistake. All right, the mistake here is I was supposed to put this as a plus, right? We see here that this is supposed to be, or sorry, this guy up here is supposed to be a plus. All right, do you guys see that mistake I made there? Let me try to fix that. Plus X. That's a mistake, right? Yeah, because we don't have any hydroxide concentration. So this is supposed to be plus. My bad, guys. It's important to check over your work and stuff too. So now let's do second calc and intersect, enter, enter, enter. And now I got X is equal to 3.46 times 10 to the negative 12, approximately, right? If I go back and I press X here, it's the same value, but yeah, just make sure you're doing it right. And so that's the value, that's the concentration of hydroxide. And that's also the concentration of, wait, what's going on here? 1 second. I actually see that I made some errors with the answer key. Oh my goodness. Oh my goodness. Wait. So, wait a minute. What did I do? What did I do wrong? Sorry, 1 second. I was looking at the answer key and it seems like I did some things wrong. Huh. Oh, I see. So he didn't like do this exactly. So that's fine. But what's next? Oh, interesting. Sorry. I think I'm doing the fine, like doing it fine actually. Yeah, I'm doing it fine. It's just I have like slightly wrong different values than him because I'm doing it with the conjugate base as opposed to the conjugate, like just the acid itself. And so the values are going to be slightly off because of that. Um, and also because I'm not using the exact number for KB here. So I'm actually doing this fine. So this is the hydroxide concentration approximately. Um, and then what's it called? The um, the other values, so HF in this case is going to be pretty much like same. So yeah, HF, or, huh, maybe I should have done. This is a very weird question, actually. Huh. Yeah, maybe I should have just done it with the Ka value. Or yikes, that's my bad, guys. Low key, yeah, I think like yeah, I don't know why that my way wouldn't work, but I guess it's because HF is remaining in the solution initially, and then you add the F minus, and because it doesn't have the same like because HF has a greater concentration than F minus, we should just consider like the Ka. So let me. This is kind of annoying. Sorry about that. I kind of confused you guys a bit with that, but yeah. So let me redo this, right? So instead, let's just do HF plus H2O, yielding F minus plus hydronium. And so we have 0.575 minus X, 0.575 minus X. Here's water. This is 0.131. Let me redo this calculation just so I can make sure I'm getting the right number. Oh, it's one. Okay, let's just do two because I didn't round it. So 132. And then hydronium is 0, so minus or plus X, 0.132 plus X, and then X. And then we can use the Ka value, which is exact, times 10 to the negative 4. And then this is equal to F minus, which is 0.32 minus X, 132 minus X over or times X. And then do 0.575 minus X. Okay, and now we redo this. I'm so sorry about this question. This question is kind of bad. I don't like this question that much, but um, I don't really think you would ask this kind of question because this question is a lot of work. Um, so let's plug this in, 0.1132 minus X times X. And then the top is going to be 6.60 times 10 to the negative 11. And then this is times by 0.575 minus X. And yeah, let's do second calc, 5. Again, I made a mistake again. This is supposed to be plus X on this Y2. That's my fault. Plus, second calc, intersect, boom, boom, boom. So I got the same X value here. I got a different X value, so 2.875 times 10 to the negative 10, which is equal to the hydronium concentration. And I can take this hydronium concentration and divide it by Kw to get the hydroxide. And then I can add the X values over there to get the other concentration. So let me do that. 0.132 plus X is this value. So it's still 0.132, right? All right, this is, why did I get such a, wait. Oh, that's my fault. Again, I guess I'm making a lot of mistakes, right? This is supposed to be 4. So like a lot of my mistakes I'm making is because I'm plugging in wrong or the approach might be wrong. Um, so let me redo this. So second calc, intersect. Okay. X value there is there. So 0.132 minus X. All right, now I'm getting some, or plus X, my fault. Now it's again 0.5. Here it's 0.575 minus X. In this case, it's going to be 0.572. The hydronium concentration, so we can figure out the pH, negative log of X is 2.55. And the hydroxide concentration is 1.0 times 10 to the negative 14 divided by X. Yikes. So that's 3.57 times 10 to the negative 12. All right. So let me just recap this one question because this was kind of a bad question. I didn't explain this question that well. So first, what we have to do is you have to find the molarity of KF. That's like the first thing. Then we can use the molarity and plug it in for K plus. That's the first value that we needed to do. Next, we need to write out a reaction and find the ice chart to figure out all the equilibrium expressions. Because HF was the thing in the solution initially, we'll just use this formula for HF. So like HF reacting with water produces F minus plus hydronium. And then yeah, you solve using the you find the ice chart, you do ice, and you get the X value, and the X value is this. And you just plug in the X values accordingly to get the final results. It shouldn't have taken as long as it did for me, but it's because I made a couple of mistakes or I didn't follow it the way that he intended it. But yeah, does anyone have any questions about this first question? That was my fault. I'm so sorry about that. Okay. All right, let me continue. So, yeah, next up, we got this barbituric acid, right? Um, yeah, so acid. The pH of this acid, so it gives off 1 hydrogen. So we can do the traditional, like we don't need to know the formula or anything. We could just HA minus or HA plus A minus yields or sorry, what am I doing? HA plus H2O yields A minus plus H3O plus to figure out the thing, right? So 0.375 minus X, 0, plus X, 0.375 minus X. And then you do this in the Ka is equal to X squared over 0.375 minus X. Ka in this case is 9.77 times 10 to the negative 5. And so then we can plug it into the calculator. So let's do here, X squared down here is 0.375 minus X times the Ka, which is 9.77 times 10 to the negative 5. And second calc, intersect, XX, enter, right? We get this X value, which is X is equal to 0.0060042 or whatever, right? Second quit, negative log of X to get the pH. So that's the pH. pH is equal to 2.22. All right, does that sound good? Let's see. What am I doing or what? Oh, it's not 375. What am I doing? Oh my goodness. I'm making like silly mistakes. These are just like, oh my goodness. So sorry, guys. Yikes. 350. Okay. So we can calc negative log of x. Sorry about that. I made some silly mistakes, but it should be fine now. 2.24. Yeah. All right. Sounds good. So this isn't the X value, but that's the pH. Now let's do this with adding potassium hydroxide. So now what we see is we have this HA is reacting with KOH, and it's producing its anion or Ka plus water. And so we could do ICF. And so we need to figure out the moles. So 0.35 times 0.05 is 0.0175 mole of acid. 0.1 times 0.075, or yeah, 0.075 is 0.0075 mole. And then we don't care about the water. And so let's see this, right? 0.075 times 0.1 is, yeah. Okay, so we see that KOH is decreasing. So we're going to do 0.0075. And this subtracts, it gets 0, right? 0.0075. And so we subtract these two values and we get 0.01 mole. And over here you have 0.0075 mole. And so with this, you have the weak acid, you have the conjugate base, and you have the Ka. So what we can do is we can do Henderson-Hasselhoff or Hasselbalch, right? And so what you want to do first is you want to figure out the concentration of both of these. And so you're going to take this mole value, divide it by 50 ml plus 75 or 0.125. So you add the two. So 0.125 liters, 0.125 liters. So this is equal to 0. Oh, where did it go? Okay, 0.06. This is equal to 0.01 divided by 0.125, 0.08. Okay. And this is molarity of HA. This is molarity of A minus. Then you just plug this in. pH is equal to pKa plus log of base, which is 0.06 over acid, which is 0.08. And yeah, and then after that, we need to figure out the Ka. So the Ka values here is 9. So negative log of 9.77 times 10 to the negative 5. And then you solve. So negative log of 9.77 times 10 to the negative 5 plus log of 0.06 divided by 0.08. And I got a pH of 3.89. All right. So yeah, I took a little bit of time to go over this. 38, I wouldn't really expect him to have like a question where he goes over all of these. I'd probably expect him to have a question regarding like, oh yeah, like what's the concentration of hydroxide or whatever. Yeah, I'd say like just make sure you're aware of like, I guess like the way he might like ask the question too. Like, yeah, he had HF in the solution, so that means that that's like the solution he's probably considering to use, or that's like the reaction he's considering to use. And then, yeah, like for 39, that's like a simple question. We've been doing this so much. And then 39B is like a titration. It's basically in between the point of A, like if this was like a titration, it'd be in between the equivalence point and the starting point. So like anywhere on this line is like where this kind of type like part B is basically. Alrighty. So I'm gonna just go over these quickly. I'm a little bit pooped. So I'm gonna try to just speed run this and then post this video, and then you guys can look at the video. All right? Does that sound good for you guys? Who's ever on Zoom?
I just had a question
Yeah.
from the 39. Like the
hmm
picture, is it meant to show you that only one H plus would like come out? Like, does it serve anything?
The picture does nothing.
Okay.
It's just being a little silly. Um, yeah, like because they gave you one Ka and they didn't specify like if it's one or two, you can assume that only one H is coming off.
Okay, got it.
Yeah, but even this picture is not doing it justice because like yeah, I'm not gonna go into it. That's like organic chemistry. This is just showing like what I guess like barbiturate looks like, I guess, or like just a compound that isn't ionized, but it's useless information. That's the whole thing.
Mhm.
Yeah. Any other questions about the last two questions? Okay. All right. So I'm gonna go over this a little bit quicker. Um, so yeah, 40 deals with strong acids and bases. So um, yeah, when you find the pH, oh, you have to mix all of these following solute. Oh gosh, that's annoying. That is really annoying. But I mean, we could just figure this out, right? So, um, yeah, the whole takeaway with this is you need to figure out the hydronium and hydroxide ions produced, right? And so when you have 25, what's it called? Let's figure out the moles that's produced with hydrochloric acid. So you have 0.025 um, times 0.25, right? So that would give you this value. So this is 0.00625 mole of H plus. With KOH, it's 0.075 times 0.15. So that's 0.01125 mole of OH minus. Okay, so is that correct? Let's see if I'm doing this math right. Okay, everything looks good. Next one is 0.02 times zero point 0.1. But with this, barium hydroxide has two hydroxides, so you do times two. Okay, so 0.004 OH minus or mole OH minus. And then here it's HNO3, so 0.03 times 0.3, so 0.009 H3O plus. So let's add the hydroniums together. So add this plus this, and I got this value. So 0.01525 mole of H plus. And then with base, it's this value plus this value. And that's also 0.01525, I believe. Let's check if I'm doing this right. So because they're both equal to one another, that saves us a lot of work. They basically cancel each other out. So the pH is 7 because these two equal one another. Okay. If it didn't equal one another, right, we'd have to figure out which one's limiting. And then from that, you'd have the moles, you have the total volume, and you have to figure out the concentration and then do negative log of that or 14 minus the negative log, depending on if it was hydronium or OH minus that was left over. All right. So 41, 42. So 41 gives you an equilibrium constant for nitrogen gas and hydrogen gas to produce ammonia. So this is N2 plus H2 yields NH3. And they're giving you the equilibrium thing. You have to balance it. So this is going to be 3 here. And the K here is 6.00 times 10 to the negative 2. calculate the equilibrium concentration of ammonia if the equilibrium concentration. All right, so this is not that bad. This is actually a pretty simple question. You don't need to make an ice chart either. You just need to know um, how to plug in these different values. So they're asking you to figure out the equilibrium concentration of nitrogen gas, and they give you or of ammonia. Ammonia is the product, so you're gonna have this as the top. So x squared over here, and you're gonna have 5.96 for hydrogen, and you're gonna have 3.15, and this is gonna be cubed. And so we can figure out this without even putting it into the graph. You could put it in the graph, but um, it's not necessary. So you do 6.00 times 10 to the -2. You're gonna get times 5.96 times 3.15, and this is cubed. All right, so that's 11, and then you do square root of 11, and that's what the x value is. So x is equal to 3.34 molarity. And let's see if that's right. Yep, so that's how you do it. So that's not that hard of a question. That takes like a minute if you read the question carefully.
Would you
All
not
right.
have to do
Yeah.
like 2x like squared?
Because they're giving you the equilibrium concentrations. You don't need to deal with like the ice chart. So like we could just do like, yeah, like this could like I like I think 2x squared like confuses things. Like it's really just like ammonium, like ammonia, right? Like
Mhm.
because like it's not an ice chart, we don't need to do that. Like we're basically plugging into the expression, which is like K is equal to like NH3 squared over H2, and then or yeah, N2 and then H2 cubed. So like we're just like plugging it in because we already know the equilibrium concentrations. There's no like initial. Also, like another key factor with that is there's no initial amounts, so there's no change. There's nothing like changing. Like when you do 2x or 3x, something's changing. Does that
Mm,
like make
yeah.
sense?
Mhm.
Yeah. Okay, sounds good. So this is asking us to find the solubility product of a saturated um, solution of this molecule. I think that's cadmium or something. So this is basically just asking us to find KSP. And so we see here that um, this is going to be GD2 SO4 3, and this is in equilibrium, producing 2 GD plus 3, I'd say, and then plus SO4 minus 2 with 3. Okay. Um, mm, yeah, this is a very interesting question, actually. So this is weird. Huh. So I believe like because they're giving you like this solubility, so this is like the solubility of the salts, right? This is this is a little misleading, right? Like this isn't the amount of salt like in the solution, or this is the aqueous amount of salt in the solution, right? So if there's 0.0673 molarity, that means that there's 2 times this here. So if we do 2 times 0.073, we're going to get 0.1346 here. And likewise, 3 times this, 0.673, or X, go back, 673 times 3. And yeah, we get 0.0, yeah, 0.2019. Okay. So yeah, with this, because it's saturated, oh yeah, okay, so yeah, saturated, and it gives you the concentration here. that is basically telling you this is the amount this is like the solubility basically within the solution. So now what we can do is we can do KSP and solve for KSP. So KSP is equal to GD plus 3, and then this is going to be squared, and then SO4 cubed, right? Like that. And so we can plug in the values. Again, you don't need to do like 2x or 3x because we already have the equilibrium amounts because they gave you the saturated solution. Yeah, so 0.1346. Here's 0.2019, and you can get the answer there. So let's do it. Clear 0.1346 squared 0.2019 cubed, and that gives you KSP value of 1.49 times 10 to the negative 4. All right, is there any questions regarding these last two questions? Or last three? All righty. All right, 43. All right, we're about to finish, so that's good. So we have a titration of methylamine, right? So this is a base, and we're given nitric acid. And so we have to do A, B, C, D. This is very similar to the question that we did in class with the weak acid and weak acid, strong base. This is now a weak base, strong acid. So let's do this, right? So A, it's going to just be the ice charts. So let's see. So this is 0. So we have this base. I'm going to just write it like that. Plus water is going to make BH plus OH minus, right? So we can figure out the hydroxide concentration and figure out the thing. We've done this kind of question before, so we can do 0.450. This is water. This is 0 minus x plus x plus x, and then 0.450 minus x, and then you do x squared over 0.450 minus x equals KB, which is 4.50 times 10 to the negative 4. Plug that in the calculator. So put that in y, x squared, 0.450 minus x, and then, yeah, we're doing 0.45. Okay, yeah, okay. 4.50 times 10 to the negative 4. Okay, and solve. So second calc, intersect, enter. Okay, you get the x value. So x is equal to this. So this is the hydroxide concentration for 14 minus negative log of x is the pH. So in this case, this pH is equal to 12.15, okay? Minus negative log. Okay, so that's the first one. So second one is going to be ICF. So we're going to do the base is reacting with the acid. So you can do HNO3 and you're producing BH plus or the conjugate acid plus NO3 minus. And you're going to do ICF. And what we'll see here is we got 0.450 times 0.05. Oh, 0.05. That's the moles of base. So 0.0225. Nitric acid is 0.1 times 0.075, or I'm just going to do 0.0075. There's nothing here, and then this is nothing, right? So like when I do this, it's going to be minus 0.0075. This is going to be running out. So this is nothing, right? And this is going to be plus 0.0075. And we get 0.0075. And then this is 0.2 or 0.0225. Yeah, minus 0.0075. So that's 0.015. Yeah, and that's the moles. And so we have the acid, we have the base, we have the Kb. So we can do the Henderson-Hasselbalch finding Ka. And so when we divide this by the volume, that's 75 plus 50, that's 0.125. This is 0.125. And this value is 0.015 divided by 0.125. That's equal to 0.12. This is equal to 0.0075 divided by 0.125. That's equal to 0.06. So acid over, or base over acid. So, and we have to figure out the Ka, right? So we do 1.0 times 10 to the negative 14. And this is divided by 4.50 times 10 to the negative 4. Okay. And this is giving you this value. So what's it called? We can plug this in, right? So negative log of Ka plus log of base, which is 0.112 divided by 0.06. And I got this value. So that's the pH. Okay, so that's the pH. pH is equal to 1.0 or 10.95. Okay, next up is C. So yeah, so C, let's do this. We're going to do an ice chart. So where did everything go? Let's go back. So again, same thing, right? B plus HNO3 yields BH plus NO3 minus. And so with this, from what I can tell, we're going to have an equal amounts, right? So 0.0225, so ICF, right? Mole. This is 0.0225. This is going to cancel each other out. And we're going to be left with 0.0225 moles BH plus. The reason why I could tell that is just because this is 225.0 and we have this amount, so I know like that's going to be the moles. You can calculate the moles on your own if you feel like you want to do that. So now we have this left over. So now we have to we have to make an ice chart. But before we do that, we need to figure out the concentration. So we have 225 milliliters plus 50, so 275. So divided by 0.275, so 0.0225 divided by 0.275, and this gives you 0.081 or 82, whatever. That's the concentration. And so now we have to do an ice chart with BH plus H2O, and that yields hydronium plus B, right? And so we need to figure out what the hydronium concentration is. So we got 0.082 minus X, 0 plus X, and then 0.082 minus X, right? We have the, we figured out what the Ka is before. So the Ka value is 2.22 times 10 to the negative 11 equals X squared over 0.082 minus X. Right? And then we have to put this into Y, or we have to put this into the calculator. So let's put this there. We do 0.082 minus X times 2.22 times 10 to the negative 11. Okay. Second, let's check if everything's right. That looks right. Okay, second calc, 5, enter. All right, so this is what X is, which is the X, this is the hydronium concentration. So negative log of this value gives you 5.87. Okay, Let's check if that's right. So it seems like it's right. Yep. Okay. So this is ICF followed by ice. And then D is when you have excess, presumably. So let's do that. So B plus HNO3 yields BH plus NO3 minus, right? So ICF 0.0225, I know that. That nitric acid is now 0.3 times 0.1. So that's 0.03. So there's excess acid now. So we can do, let's go back. Sorry about that. I'm almost done. Yeah. So this is going to be 0.075 or 0.0075. Sorry, we're going to do 0.0225, 0.0225, right? Subtracting both of these is going to get you 0.075 mole of HNO3. And then from there, we can figure out the concentration of nitric acid. So that's 300 plus 50. So do 0.35 and do 0.0075 divided by 0.35 to get the concentration of HNO3. So 0.0214. And we could do the negative log of this to get the last concentration. So let's do that. And I got 1.67. Oh, great. That's how we ended off. That's the right answer. So pH equals this 1.67. This is probably the longest question you're going to encounter. However, there's a lot of steps that are involved, right? Before anything's added, that's ice. When it's between the like if I were to draw out the equivalence point or like a titration, this is like A basically. B is like somewhere in between the equivalence point and A. C, right, was the equivalence point. So that's why there was conjugate acid left over, and then D is afterwards. And so yeah, there's like if you know all three of those things, you can figure out like methods to do this. So B is ICF followed by Henderson. C would be ICF followed by ice. And then D is ICF followed by just negative log of whatever you have left over. All right. Yeah, is there any questions regarding this? All right. If not, I'm gonna get going. That was quite a lot for me, but I will post this on YouTube and email it to you guys um before anything, you know. And yeah, tomorrow we have our SI session at 3:30, I believe. So yeah. If we'll be going over the next exam, like yes, last year's exam. So yeah, with that, I'm gonna say goodbye. Thank you guys for joining me. Have a good day. Bye-bye.